Now we come to the example where the surface sound intensity is non-uniform, right? So we have pretty much the same setup up to this point. We have sigma dA, and dA is 2 pi r prime dr over 4 pi divided by this radius squared, right? So at this point, what's going to happen, the 2 pi is going to come out, the 4 pi is going to come out, then you're going to have here sigma r prime dr prime over 9 plus r prime squared, right? And then the difference is that in this case the sigma will not come out, right? You have to put the function. So in this case it's telling us that the sigma changes as r prime squared. That means as the radius of the sphere increases, the sound intensity gets more denser. That means the outer edges of the speaker are louder than the inside portion, right? So, and the function is a square. This function could have been anything. It could have been a linear function, it could be square, it could be cubic, it could be to the fourth. It could even be a decreasing function. Sigma is equal to alpha r prime to the minus 1. What that would mean is that the inside portion of the speaker would be louder than the outer portion of the speaker, right? So you can have any kind of random function of r, and then you can apply the same theory, right? So then we're going to put the sigma function over here and make it alpha r prime squared. So then the alpha will come out of the integral, and then you have here I alpha, and then this will be 1/2. So alpha over 2, right? And then the inside of the integral is going to be what? R prime cubed over 9 plus r prime squared dr prime, and then you got 0 to 6 over pi, right? The total radius of the plate was 6 over pi. Then we're going to have to calculate what the alpha is. So now let's do the integral, right? Then we're going to have to multiply that by alpha over 2. But what does alpha have to be in order to make the total sound power of the speaker 100 watts? So we're going to have to do another integral to calculate for the alpha, right? So we have here sigma dA is equal to dP. Then we have here sigma is equal to alpha r prime squared. dA is equal to 2 pi r prime dr prime. So dA is always the area of a ring, which is the circumference of the ring, which is the circumference of the ring is 2 pi r prime, and then times the thickness of the ring, which is dr prime. So that's what this is doing, multiplying the circumference of the ring by the thickness of the ring, and then this is the function for the sigma, and then that's equal to dP, right? R prime cubed is going to be r to the fourth over 4, r to the fourth over 4, then you go 0 to 6 over pi, and that's equal to p, right? So 2 pi alpha over 4, 6 over pi, and then to the raised to the power 4, and then that's equal to p. So this will tell us what the alpha needs to be in order to make the total power of the speaker 100 watts, right? So, and then one of the pi's will cancel the pi to the fourth, which is going to make it pi cubed, right? And then that's going to equal to the power p. So then alpha is going to have to be equal to what? 2 times the power, right? Times pi to the power cubed over 6 to the power 4. And that's it. There's no 10 to the minus 1 or anything. So, okay? Is that smaller or larger than the uniform one? Well, actually, it's a bit smaller. The other one was a 118 point something. It was a decimal larger than 0.45. I believe it was 118.6 or 0.7. So it was definitely larger. So what's happening here is the answer making sense. Well, if the speaker is non-uniform and it's circular, it means the louder portion is at the edge, right? Like this. And then if you're sitting here and you are farther away from the larger portion, you should be a little bit, the sound intensity should be a little bit less louder than if it was uniform, right? If it was, since the sound intensity is uniform, your distance from the middle portion is closer than the outer portion, but the middle portion is not any weaker than the outer portion, right? So this person should be hearing a louder sound than this person because distance here is farther away from the outer edge, which is the louder portion, okay? So you can see here from this argument that this one should be a little bit less loud, and it did come out to be a little bit less in decibels, okay? So that kind of completes the rod, the semicircle, and then semicircle away from the center, the ring, and then the plate, okay? And then you can apply this to many different kinds of problems, and you can even apply it for electricity, you can apply it for electric potential, and you can also apply it for gravity too. So these kind of problems have a lot of different applications in different areas in physics, okay? Thank you very much.